Okay, so now that you've had some practice solving motion problems using kinematics equations, let's look at the special case of objects that are moving on an inclined plane. So in AP physics, it's pretty common on the test to be presented with a scenario like this, where you have an object that is sliding or rolling on a ramp surface like this. And here's what's different about it. The object, all the displacement, the velocities, the accelerations are constrained to this plane. The object cannot move up or down. It cannot move right or left. It can only move parallel to this inclined surface. And so that makes a slightly different scenario, but fortunately not too different. There's just a couple strategies we need to solve these problems. And once we learn these strategies, they're really no different than the other kind of kinematics problems. So let's get on it. So one of the first things you have to do in working with a ramp problem is decide what you're going to call the positive direction. And here's a bit of advice for you that I got from a really good physics professor many years ago, and that is, you know what? Set the direction of initial motion as positive. If you do that, you'll usually make your life a lot easier. So in this case here, I've got an object with its initial velocity is up the ramp. So I'm going to call the up ramp direction positive, and therefore the down ramp direction is negative. If I was to release the object, it would accelerate in the down ramp direction because of gravitation. So acceleration is in the negative direction. If the object is up here moving down, that's moving in the negative direction. This displacement is up the ramp, so that would be in the positive direction. So let's consider this. So the only real trick to these inclined plane problems is to keep in mind that that inclined plane affects the rate of acceleration of gravity. If the plane was inclined 90 degrees to the surface, to a table surface, then this object would simply accelerate at g, at 10 meters per second squared. But if I tip it a little bit, so now this plane makes an angle of 70 degrees with respect to the table surface, this is preventing it from accelerating as fast as gravity would have it accelerate. So it's going to accelerate a little bit less, in this case, 9 meters per second squared. If I drop it a little bit more to a 45-degree angle, that does not mean it's going to go half as fast, but it's going to end up traveling at 7 meters per second squared. And if I drop it down to 20 degrees, it would travel at 3.4 meters per second squared. It just randomly chose these numbers. Now, clearly, there's some trigonometry that might come into play here. And so let's just do a very quick review of Sohcahtoa. I'm sure most of you are pretty familiar with it, but it's always worth reviewing. So whoever came up with Sohcahtoa should get a Nobel Prize posthumously because it's genius. Okay, so the bottom line is the sine of an angle is going to be the so part is opposite over hypotenuse. The cosine or ca is going to be adjacent over hypotenuse. So this length over this length. And the toa would be the tangent is equal to opposite over adjacent. And this is basically not exactly challenging trigonometry, but it's very commonly encountered in AP physics. So we just need to start practicing it. All right, so let's look at a situation like this. I got theta here. I've got 4 meters high. 안녕하세요. Got 8 meters long. So if I want to find the sine of this angle, I would simply say, well, the sine of this angle is going to equal opposite over hypotenuse, 4 over 8, or 1/2. But what if I had this instead? So now I've got the theta is up here. In this case, the 4 and 8 have different values. This is now my adjacent value, and this is still my hypotenuse. So in that case, it would be cosine equals adjacent over hypotenuse. And in that case, the cosine of this angle would be 1/2. Um, and then if I come over to here, I just want to point out a very, very common setup is this. I know this angle here, and I want to know this value here based on this value here. It's a really common thing in physics. I know this value, I know this angle, I want to find this value. Well, so I'd say this, well, this is the opposite, so I'm going to use sine. So I would say the sine of 30 equals 4. Now, if you go back over here, look, if I just took this one here, let's ignore this equals 1/2 part here, if I just say sine theta equals 4 over 8, if I just move the 8 over to here, I'd say 8 times sine theta would equal 4, which is the height here. And that is just a scenario that comes up quite often in AP Physics. Okay, now when we're working with angles, sometimes we'll want to work with degrees and sometimes we'll work with radians. Mostly we'll work with radians when we're talking about rotational motion. But for the rest of the year, which is almost all of the year, we're going to be using degrees. And so you'll probably want to use the degree mode in your calculator. So if you enter a number into your calculator, you got to make sure that you're in degrees mode rather than radian mode. And so the easiest way to check that is just take the sine of 90. So if you say sine 90, enter. If you get 1, you're in degrees. If you say sine 90 and you get 0.8939, you're in radians. You need to change it. So just remember, the sine of 90 should be 1. Okay. And here's what's useful about it. Now, if on your AP Physics sheet, when you look at it, it will give you these values here. All right. So it will say here the trigonometric functions for common values. And if you look here, the people at College Board are saying to you, look, we're only going to give you these angles. We're going to give you 0, 30, 45, 60, 90, and we might give you 37 and 53. But what's nice about this is that we're giving you what the values are, so you wouldn't even have to use your sine or cosine function on your calculator if you didn't want to. Instead of saying the sine 30 degrees, you could just type in 1/2. Instead of saying sine 37 degrees, you could just say 3 divided by 5. So they're giving you the values of these trigonometric functions for particular angles, and these are the only angles that College Board is going to ask you about. So it's just a shortcut that you can use. You don't have to, but you can. Now, by the way, on the test, on both sections of the test, MCQ and FRQ, you are allowed to use your calculator. You are allowed to use your TI Inspire. I personally am more fond of TI 84s, but that's okay. I'm a dinosaur. All right, let's just take a look at this. Let's say I was asked to find the value of H. Well, this is just the problem we looked at before. I'm going to say this times the sine of this is going to equal this. So if I say 8 times the sine of 45 on my calculator, as long as I've got it in degrees and not radians, the answer I'm going to get is 5.66 meters. But let's just say I didn't want to use the sine function on my calculator. I just wanted to go back and look at that trigonometric table from over here. Whoops, over here. I say, oh, well, the sine of 45 is square root of 2 over 2. So if I just say, okay, well, 8 times the square root of 2 over 2, I get the same value. So it's just a way of, I suppose, just making it a little bit easier to calculate. Also, too, sometimes when we're trying to solve things for express this in terms of that, it's a little bit cleaner to do it this way. Okay, so how does this apply to ramps? Well, here's the deal. It has to do with figuring out what the acceleration is going to be. And the easiest way I can describe this to you is this. If I take a 90-degree angle with respect to the table surface or floor surface, and I take the sine of 90, sine of 90 is 1. 1 times gravitational acceleration is gravitational acceleration. 1 times 10 meters per second squared is 10 meters per second squared. An object is going to go down this ramp as though there was no ramp, right? So basically, g sine theta, that is how fast an object is going to accelerate on an inclined surface. What's the sine of 0? Well, the sine of 0 is 0. Okay, so if I say 0 degrees, sine of 0 degrees times 10, I'm going to get 0. This object is not going to accelerate. Things on a flat surface don't accelerate. I put it at a 45-degree angle. Well, g times the sine of 45 is 7.07. That's how fast it'll accelerate. And if I put the sine of 30 degrees, you're going to memorize this before the year's over. The sine of 30 degrees is 0.5, so the object is going to accelerate at half the normal velocity on the surface. So basically, it's really important for you to get used to the idea that on an incline, acceleration isn't equal to g, it's equal to g sine theta. All right, so here, let's just go through a problem here. I've got an object that's initially located at point P on an incline. The incline has a 30-degree angle to it. The object is initially moving up the ramp at 5 meters per second, and I've been asked to figure out where will the object be 3 seconds later. So let's look at what I know here. Okay, I know it's accelerating. I know the initial velocity, and I'm asked about where it's going to be, which is displacement and time. So I think I know which kinematic equation I'm going to have to look at. I know I've got VI, I've got A. Now, careful. Now, look here. The object is moving up. So I'm going to set up as the positive direction. Well, g sine theta is going to be in the downward direction. So I'm going to say negative 10 sine 30 is negative 5 meters per second squared. I know time is 3, and I'm looking for delta x. And delta x could be positive or negative, depending on the values I've been given. So let's just try this here. This is the appropriate kinematics equation to use because I'm asked about displacement, I'm told about velocity, I'm told about time, and I know acceleration. And notice, I didn't say anything expressly about acceleration here. We are to understand that this object is going to undergo gravitational acceleration, and since it's on an incline, it's going to be g sine theta. So if I go ahead and substitute in, all right, what I'll find is I have positive 5 meters per second because it's moving up times 3 seconds, plus 1/2 of negative 5 meters per second squared because it's going to accelerate in the downward direction, times 3 seconds squared. I get negative 7.5 meters, meaning that the final position is in the 7.5 meters in the negative direction from point P, which means it's going to be 7.5 meters down in this direction here. All right, let's try another one of these. All right, so I have this object that's being projected up a ramp. This ramp is 6 meters long. It has an angle of 45 degrees with an initial velocity. I don't know what it is, but I know it leaves the top at 8 meters per second. So I want to know what is the initial velocity. So in this case, I have a distance, I have an acceleration because I know there's gravity, and I have an initial velocity and a final velocity. I don't have any information about time. Okay, so basically, I'm going to set the up direction as positive, so gravity is therefore going to be negative. All right, so I'm going to say acceleration is equal to g sine theta. G is going to be negative 10 in this case, so I get negative 7.07 meters per second squared. The final velocity is 8 meters per second. The displacement is 6, and I'm looking for the initial velocity, so it's going to be this old equation here. Final velocity squared equals initial velocity squared plus 2a delta x. Let's just substitute in our values. And remember, I have a negative value for acceleration here. And what I end up getting is it started off at 12.2 meters per second, and it left the top at 8 meters per second. Well, let's move away from numbers and just try to solve for things in terms of variables. That's a very, very common type of question to get on your AP Physics exam, and we just need to practice them all year long. So an object slides down a ramp of length L, that is oriented at angle theta with respect to the horizontal. Express the velocity of the object at the bottom of the incline in terms of LG and theta. Don't panic. You just say, okay, well, let's see here. What is it I want to know? I want to know the final velocity of an object that started from rest. Well, that's a velocity. I know what the distance is, and I know what the angle is. I know what G is. All right, so that means I know which equation I've got to use. It's this one again, right? Because my initial velocity is 0 right here. I'm looking for my final velocity. I know the distance is L, so delta x in this case is L, and A is going to be g sine theta. Now, in this case, when I let go of it, it's going to move this way. So I'm going to call this the positive direction. I don't have to, but I'm choosing to. All right, it just makes my life a little bit easier to do that. So I'm going to say this is the positive direction. And so I'm going to say the final velocity is going to equal 0 squared plus 2 times sine theta GL, or g sine theta L. All right. Now, I want to rearrange this then to solve for, since this is 0, I'm going to get rid of that. I want to take the square root of both sides to get rid of that. And so what I get is the final velocity is going to equal to root 2 sine theta GL. Or I could say root 2g sine theta L, either way. Okay, so what if I had this question? What if I was asked, I forgot to put in, I gave it away before I got to hit the buttons, darn, okay. What if I was told, okay, so it gets to the bottom at speed v. What if the length was twice as long? How fast would it be then, right? So I would say, well, I've already established using that last equation that the relationship is the v final is going to be equal to root 2 sine theta GL, all right? And so remember, when I'm trying to do proportionality, everything that's not what I'm interested in remains constant. I can just make it a 1. So all of this here, none of this changes. The 2 doesn't change, the sine doesn't change, the theta doesn't change, and the G doesn't change. The only thing that changed was the L and the V. So that means V final is proportional to the square root of L. Therefore, if I double L, then V is going to go up because they're both in the numerator, is going to go up by root 2. So basically 1.4 times faster. All right, how about this? I have one end of a table that's lifted 50 centimeters above the floor. A card is released from the top. Now, if it's released, that means its initial velocity is 0, so that's a known value. At a position 3 meters away from the lower end of the table surface, how long will it take to reach the bottom edge of the table surface, assuming that friction is negligible? By the way, this is a really common convention used in physics. The deal is there's always going to be friction, okay? And so they used to say, assume a frictionless surface. And people say, well, there's no such thing. So, okay, so we're going to say, assume friction to be negligible. Bottom line is, unless you're told to pay attention to friction, ignore friction. If they want you to pay attention to friction, they will make it very clear to you. We'll talk more about friction later on. So I'm going to make a sketch. It's always a good idea. So basically, it's 0.5 meters high. I don't know what this angle is here. I know that this is 3 meters long. And so what I want to know is what the time is going to be when it reaches this point here. All right, well, let's see. I know it's accelerating at g sine theta. Gosh, it'd be great if I knew what theta was, all right? So I can say is, okay, well, I know delta x. I know that a is g sine theta. Let's figure out what g sine theta is, because I can't answer this until I know that. Well, so this is the equation I'm going to need to use, but I've got to figure out what a is going to be. All right, so a is going to be g sine theta. Now, can I figure out what that is? Well, in this case, I'm going to say, well, the definition of sine theta is opposite over hypotenuse, right? So it's going to be 0.5 over 3. I'm just going to, instead of saying sine theta, I'm just going to put in that identity. And so it makes it pretty straightforward then. As long as I remember my Sohcahtoa, it does at least. So even though I don't have to be told what this is, I can figure it out using trigonometry. And now there's just one unknown variable. So then I'll solve for it, and I get t equals 1.897 seconds. By the way, I should point out, in AP Physics, there is no requirement that you pay attention to significant figures. It's best you show your work, you write your answer out. It's best, I would say, give yourself 3 or 4 digits if it keeps going. Don't slavishly write down 20. That'd be silly. But there's no points taken off or awarded for using or not using the correct number of significant figures. Although your chemistry teacher might be mad if you don't. All right, one last one. I'll let you go, promise. Okay. So now I have a cart moving up an incline at 30 degrees. It's got initial velocity 10 meters per second. I want you to draw the following motion graphs. Now, that's another common thing we're going to be asked to do a lot in AP Physics. So let's just practice it. It's actually not so hard, okay? So I want to make motion graphs for acceleration, velocity, and position. And by the way, I want to identify maxima, minima, intercepts, and slopes, okay? Let's just try this here. All right. So I know that this object is going to accelerate since this is the positive direction, this is going to be the negative direction. So I'm going to say it's going to be accelerating at g sine theta. This should say a negative here. So it's going to be negative 5 meters per second squared as my acceleration. So it's pretty easy to make an acceleration graph. I just say, and often we have this graphs like this. They're not labeled with any numbers. That's a pretty common setup in AP Physics. You're just going to get 2 axes, no numbers on them, and they just want you to give a general sense of the shape of the graph, and then you're going to label, in this case, the y-intercept, okay? So we say, oh, okay, well, so this is going to be just a constant acceleration of negative 5 meters per second, regardless of whether this object is rolling up or down the ramp. Let's go on and look at velocity. So if I'm going to look at velocity, I've got to figure out, like, well, how long does it take this object to stop and then come back? So I'm going to use this equation here to figure out how long it takes this object to move up the ramp. So basically, I'm accelerating at negative 5. My final velocity, when it reaches the highest point that it's going to get to, will be 0. It'll stop there momentarily. And then 10 is going to be the initial velocity, which is, you remember that it's minus, so I'm minusing a positive number. And I'm going to solve that for t. And when I do that, I get 2 seconds. That means in this situation, this object will move upwards for slowing down for 2 seconds. It will stop, and it will come back down for 2 seconds. So it should take it 4 seconds to return to this position after reaching its high point at time t equals 2 seconds. So when I draw my velocity versus time graph, it's going to be a constant slope, because a constant slope indicates a constant acceleration. It's a negative slope indicating a negative acceleration. And I'm going to label that slope negative 5 meters per second squared. Okay, so AP Physics test readers, I know I calculated the slope. Now, it started off at 10 meters per second, so the initial velocity, this is times zero, so at time zero, its initial velocity was 10 in the positive direction, so I'm going to put it here. Now, when did it reach a velocity of zero? When did it stop? Well, I just did this work here so I could label this x-intercept. So at time t equals 2 seconds, that's when it crossed the x-axis at zero velocity. And then it started accelerating, then it started moving in the downward direction at increasing velocity, and it finally reached negative 10 meters per second after 4 seconds of travel. All right, now we're going to do our position versus time graph. So now I have to know how high up this ramp, how far up this ramp did it go? I haven't figured that one out yet, so I better do that. So in this case, I know that the final velocity is 0. I know the initial velocity is 10. I know what A is. It's g sine theta. And I want to figure out what this delta x is. That's going to be the length that it travels up the ramp. All right, so let's just do it. All right, so I know that the final velocity is 0, that the initial velocity is 10, that g sine theta is negative 5 meters per second squared. So I just solve it for delta x, and I come up with 10 meters. This object is going to go 10 meters up the ramp. In 2 seconds, it's going to stop. And in 2 seconds later, it's going to come back down another 10 meters back to where it started after a total of 4 seconds. So when I graph that, I put this here for a reason. I got this value here by using this equation. However, I could have done it a different way. And the AP physics readers would be perfectly happy if we did this. I could say, well, instead of using this equation, I'm just going to use the area here, right? The area under the line in a velocity versus time graph. Remember, meters per second times seconds is just meters. So this area here is going to be the positive displacement, how far it went in the positive direction. So if I said, I made a rectangle, 10 meters per second times 2 seconds, but it's half that rectangle. That's 20 divided by 2 is 10. I could have done it either way. Now I'm going to go ahead and draw my graph. So in this case, I know that the maxima is going to be at 10 meters. And I'm going to represent it this way, a little line showing that that's what it is. I could write 10 meters here if I wanted. I'm going to indicate that this was reached at time 2 seconds, and that it came back down to its initial position at 4 seconds. Hey, thanks for watching. Sorry this one took a little bit of time. We'll practice in class. You'll see they're really not that intimidating after all.